Hi, my name is Rick Lineker, and this is for CIS 3360 at University of Central Florida. Let's start off by defining security. The security of a system, application, or protocol is always relative to a set of desired properties and an adversary with specific capabilities. For example, standard file access permissions in Linux and Windows are not effective against an adversary who can boot from a CD. So we commonly use an acronym, CIA, to describe security goals. And CIA stands for Confidentiality, Integrity, and Availability. Confidentiality is the avoidance of the unauthorized disclosure of information. Confidentiality involves the protection of data, providing access for those who are allowed to see it, while disallowing others from learning anything about its content. Encryption, the transformation of information using a secret called an encryption key, so that the transformed information can only be read using another secret called the decryption key, which may, in some cases, be the same as the encryption key. And here you see a diagram of the sender encrypting the plain text, sending it over a communication channel, and the recipient decrypting it with the same shared secret key. Access control provides rules and policies that limit access to confidential information to those people and/or systems with a need to know. This need to know may be determined by identity, such as a person's name or a computer serial number, or by a role that a person has, such as being a manager or a computer security specialist. Authentication is the determination of the identity or role that someone has. This determination can be done in a number of different ways, but it is usually based on a combination of something the person has, like a smart card or a radio key fob storing secret keys, or something the person knows, like a password, or something the person is, like a human with a fingerprint or retina scan. Authorization is the determination if a person or system is allowed to access resources based on an access control policy. Such authorization should prevent an attacker from tricking the system into letting him have access to protected resources. Physical security is the establishment of physical barriers to limit access to protected computational resources. Such barriers include locks on cabinets and doors, the placement of computers in windowless rooms, the use of sound dampening materials, and even the construction of buildings or rooms with walls incorporating copper meshes, sometimes called Faraday cages, so that electromagnetic signals cannot enter or exit the enclosure. Integrity is the property that information has not been altered in an unauthorized way. Some tools for this include backups, the periodic archiving of data, checksums, the computation of a function that maps the contents of a file to a numerical value. A checksum function depends on the entire contents of a file and is designed in a way that even a small change to the input file, such as flipping a single bit, is highly likely to result in a different output value. Data correcting codes are methods for storing data in such a way that small changes can easily be detected and automatically corrected. Availability is the property that information is accessible and modifiable in a timely fashion by those authorized to do so. Tools for this include physical protections, infrastructure meant to keep information available even in the event of physical challenges, and computational redundancies, computers and storage devices that serve as fallbacks in the case of failures. Three other very common security concepts can be represented by the acronym AAA. This stands for assurance, authenticity, and anonymity. Assurance refers to how trust is provided and managed in computer systems. This depends on policies, which specify behavioral expectations that people or systems have for themselves and others. For example, the designers of an online music system may specify policies that describe how users can access and copy songs. Permissions, which describe the behaviors that are allowed by the agents that interact with a person or system. For instance, an online music store may provide permissions for limited access and copying to people who have purchased certain songs. And finally, protections, which describe mechanisms put in place to enforce permissions and policies. We could imagine that an online music store would build in protections to prevent people from unauthorized access and copying of its songs. Authenticity is the ability to determine that statements, policies, and permissions issued by persons or systems are genuine. Primary tools for this are digital signatures, which are cryptographic computations that allow a person or system to commit to the authenticity of their documents in a unique way that achieves non-repudiation, which is the property that authentic statements issued by some person or system cannot be denied. Anonymity is the property that certain records or transactions not to be attributable to any individual. Tools for this include aggregation, which is the combining of data from many individuals so that disclosed sums or averages cannot be tied to any individual. Mixing, which is the intertwining of transactions, information, or communications in a way that cannot be traced to any individual. Proxies, which are trusted agents that are willing to engage in actions for an individual in a way that cannot be traced back to that person. And finally, pseudonyms, which are fictional identities that can fill in for real identities in communications and transactions, but are otherwise known only to a trusted entity. So let's talk about some threats and attacks. Let's start with eavesdropping. This is the interception of information intended for someone else during its transmission over a communications channel. And here you see the classic illustration with Alice and Bob in a conversation and Eve somewhere in the middle listening in. So alteration is the unauthorized modification of information. So an example of this is man-in-the-middle attack, where a network stream is intercepted, modified, and transmitted. And here you can see the plain text is encrypted, sent over the communication channel, and there's an attacker that intercepts it and transmits a different version, and then the recipient decrypts it, getting a different plain text than the original sender sent. Denial of service is the interruption or degradation of a data service or information access. So an example of this might be spam, email spam, to the degree that is meant to simply fill up a mail queue and slow down an email server. Masquerading is the fabrication of information that is purported to be from someone else who was not actually the author. In other words, if something says it's from Alice but is really from Eve. Repudiation is the denial of a commitment or data receipt. This involves an attempt to back out of a contract or a protocol that requires the different parties to provide receipts acknowledging that the data has been received. Correlation and traceback are the integration of multiple data sources and information flows to determine the source of a particular data stream or piece of information. Now let's talk about 10 security principles: economy of mechanism, fail-safe defaults, complete mediation, open design, separation of privilege, least privilege, least common mechanism, psychological acceptability, work factor, and compromise recording. Economy of mechanism is a principle that stresses simplicity in the design and implementation of security measures. While applicable to most engineering endeavors, the notion of simplicity is especially important in the security domain, since a simple security framework facilitates its understanding by developers and users and enables the efficient development and verification of enforcement methods for it. Fail-safe defaults. This principle states that the default configuration of a system should have a conservative protection scheme. For example, when adding a new user to an operating system, the default group of the users should have minimal access rights to files and services. Unfortunately, operating systems and applications often have default options that favor usability over security. This has been historically the case for a number of popular applications, such as web browsers that allow the execution of code downloaded from the internet on a web server. Complete mediation is the idea behind the principle. This is that every access to a resource must be checked for compliance with a protection scheme. As a consequence, one should be wary of performance improvement techniques that save the results of a previous authorization checks, since permissions can change over time. For example, an online banking website should require users to sign on again after a certain amount of time, say 15 minutes, has elapsed. Open design. According to this principle, the security architecture and design of a system should be made publicly available. Security should rely only on keeping cryptographic keys secret. Open design allows for a system to be scrutinized by multiple parties, which leads to the early discovery and correction of security vulnerabilities caused by design errors. The open design principle is the opposite of the approach known as security by obscurity, which tries to achieve security by keeping cryptographic algorithms secret, and which has been historically used without success by several organizations. Separation of privilege. This principle dictates that multiple conditions should be required to achieve access to restricted resources or have a program perform some action. Least privilege. Each program and user of a computer system should operate with the bare minimum privileges necessary to function properly. If this principle is enforced, abuse of privileges is restricted, and the damage caused by the compromise of a particular application or user account is minimized. The military concept of need to know information is an example of this principle. Least common mechanism. In systems with multiple users, mechanisms allowing resources to be shared by more than one user should be minimized. For example, if a file or application needs to be accessed by more than one user, then these users should have separate channels by which to access these resources to prevent unforeseen consequences that could cause security problems. Psychological acceptability. This principle states that user interfaces should be well designed and intuitive, and all security-related settings should adhere to what an ordinary user might expect. Work factor. According to this principle, the cost of circumventing a security mechanism should be compared with the resources of an attacker when designing a security scheme. A system developed to protect student grades in a university database, which may be attacked by snoopers or students trying to change their grades, probably needs less sophisticated security measures than a system built to protect military secrets, which may be attacked by government intelligence organizations. Compromise recording. This principle states that sometimes it is more desirable to record the details of an intrusion than to adopt more sophisticated measures to prevent it. Internet-connected surveillance cameras are a typical example of an effective compromise record system that can be deployed to protect a building in lieu of reinforced doors and windows. The servers in an office network may maintain logs for all accesses to files, all emails sent and received, and all web browsing sessions. Okay, so let's talk about access control. The groups that this talks about are users and groups, authentication, passwords, file protection, access control lists, and these seek to address the following question. Which users can read, write which files? Are my files really safe? What does it mean to be root? And finally, what do we really want to control? So we have this idea called access control matrices. This is a table similar to an Excel spreadsheet that defines permissions. Each row of the table is associated with a subject, which is a user, group, or system that can perform actions. Each column of the table is associated with an object, which is a file, directory, document, device, resource, or any other entity for which we want to define access rights. Each cell of the table is then filled with the access rights for the associated combination of subject and object. Access rights can include actions such as reading, writing, copying, executing, deleting, and annotating. An empty cell means that no access rights have been granted. So here's a matrix. You see on the left side you see the users, and the top column is the folders which you're gonna set permissions for. Now each cell in the grid determines what permissions that the user and the resource have. An access control list defined for each object O, a list L called O's access control list, which enumerates all the subjects that have access rights for O. For each such subject, S gives the access rights that S has for object O. In a sense, this is similar or has similar information than the matrix, but it's just structured and organized in a slightly different way. Capabilities. This takes a subject-centered approach to access control. It defines, for each subject S, the list of the objects for which S has non-empty access control rights, together with the specific rights for each such object. And here again, it's the same information, just structured differently, because structuring things differently has advantages in different settings. The last thing is role-based access control. This defines roles and then specifies access control rights for these roles, rather than for subjects directly. So now let's talk about cryptographic concepts. Encryption is a means to allow two parties, customarily called Alice and Bob, to establish confidential communication over an insecure channel that is subject to eavesdropping. And we've already seen this image illustration before in this set of slides. Alice and Bob are having a normal conversation while Eve is listening in. The message M is called the plaintext. Alice will convert plaintext M to an encrypted form using an encryption algorithm E that outputs a ciphertext C for M. So C, M, and E are going to be common symbols for us to remember. So here in this diagram you see the sender encrypting the plaintext using a shared secret key. It's sent over a communication channel and the recipient decrypts it with the same secret key. And you get the plaintext exactly like the plaintext that was encrypted. So you have two equations. C, which is a ciphertext, equals the encryption of the plaintext. And finally, after that, the plaintext equals the decryption of the ciphertext. So the encryption and decryption algorithms are chosen so that it is infeasible for someone other than Alice and Bob to determine plaintext M from ciphertext C. Thus, ciphertext C can be transmitted over an insecure channel that can be eavesdropped by an adversary. So this is the different segments of a crypto system. The set of all possible plaintexts, the set of all possible ciphertexts, the set of encryption keys, the set of decryption keys, the correspondence between encryption keys and decryption keys, the encryption algorithm to use, the decryption algorithm to use. So this is a really old type of encryption method called the Caesar cipher. And this replaces each letter with 1, 3 over in the alphabet. For instance, A plus 3 is D. So A encrypts to D, B encrypts to E, and F encrypts to F. So C plus 3 is C, D, E, F. Okay? And you might notice the ghosting has X, Y, and Z because when you get to the end, you're still going to have to add 3, and that's how we end up doing that. So symmetric cryptosystems are slightly different. Alice and Bob share a secret key which is used for both encryption and decryption. Right? They share the same shared secret key, which Alice uses to encrypt the data, send it over the channel, and Bob uses the same key to decrypt it. So this requires each pair of communicating parties to share the secret key. Maybe the secret key is a password, Maybe it's something else, but normally it's a password. Public key cryptography is quite different though. Bob has two keys, a private key and a secret key. Okay, Bob broadcasts the public key widely. He has no problem. Normally a public key is maybe your username or something. So in order for Alice to send an encrypted message to Bob, she need only obtain his public key. Use that to encrypt her message, M, and send the result, ciphertext equals E of M to Bob. Bob then uses his secret key to decrypt the message, such as plain text equals decryption of C, the ciphertext. Separate keys are used for encryption and decryption when you're talking about public key cryptography. Okay, so this is where your plain text is encrypted using a public key. It goes over the communication channel, and then the recipient uses a private key to decrypt it. Public key distribution is where only one key is needed for each recipient. So digital signatures are public key encryption provides a method for doing digital signatures. To sign a message, plain text M, Alice just encrypts it with her private key, creating the ciphertext. Anyone can decrypt this message using Alice's public key, such as M prime equals the decryption of the ciphertext, and compare that to the message M, which is the original plain text. A checksum on a message M, that is, one way, it should be easy to compute, but hard to find M given only Y. It should be collision resistant. It should be hard to find two messages M and N such that they both have the same values. And examples of these hashing functions are SHA-1 and SHA-256. And these have been around for quite a few years. So now let's talk about message authentication codes. This allows for Alice and Bob to have data integrity if they share a secret key. Given a message M, Alice computes a hash and sends the plain text in this hash to Bob. Okay, and here you see the message she's sending, the plain text and the hash. Digital certificates. These are provided by a certificate authority which digitally signs a binding between an identity and the public key for that identity. Passwords. These are a short sequence of characters used as a means to authenticate someone via a secret that they know. Here you see user ID and password. So how a password is stored, normally in a database or a password file. So let's say this user has a password of dog124, and that password is hashed, and while the password itself is not stored in the password file, but the hash itself is stored in the password file. That way you can't open up the password file and see what the actual password is. Strong passwords. A strong password has upper and lower case characters, special characters, and numbers. So out of these next four, which are strong? Seattle 1 is almost strong, but there's no special character. Mike 03 is strong, no special characters, but this third one is very strong because it has upper, lower, special characters, and a single digit. And the last one would be very strong, except for it doesn't have a special character. So here's a way to sort of calculate password complexity for numbers. Just simple numbers, you're going to get about 1 million. When you do upper or lower case characters, you get about 308 million. When you do upper and lower, you get about 19 billion. And when you have 32 special characters, you get about 1 billion. So odd characters make passwords safer. And password length itself lends a lot to the potential security of a password. You see here 5 characters, you might have approximately 7 billion, 6 characters, approximately 689 billion, and so forth. The longer the characters, the more secure your password is. Longer passwords are better. However, they are very impractical, so you got to kind of balance the risk versus the security versus the convenience. Password validity brute force test. Okay, and this will tell you what it would take to crack passwords of 5, 6, 7, 8, and 9 length. So secure passwords. A strong password includes characters from at least 3 of the 4 groups. use passphrases if you want to try to remember things. So this is a very strong passphrase, and it would be virtually impossible to crack with brute force. So the last thing I want to talk about is social engineering. Sometimes they use pretexting, which is creating a story that convinces an administrator or operator into revealing secret information. Baiting is offering a kind of gift to get a user or agent to perform an insecure action. And quid pro quo, offering an action or service and then expecting something in return.